Welcome everyone to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for UW Extension and Cooperative Extension. And on behalf of those folks and our other co-organizers, Wisconsin Public Television, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce to you Lennon Rodgers. He's with the Grainger Makerspace here in the College of Engineering. He was born in Sterling, Illinois, which is 12 miles from Dixon, Illinois, and we are rivals. He went to school at Sterling, Illinois High School, which means he was a Golden Warrior. Then he went to the University of Illinois and studied mechanical engineering for his undergrad. He went to MIT at 2 different bouts, first to get his master's degree in mechanical engineering, and then he went back to get his PhD in mechanical engineering. He spent 2 years in Switzerland and then came back to MIT to work 2 years there. And then about 1.5 years ago, he came to UW-Madison to help open the Grainger Makerspace, where he is the director. Tonight, he gets to talk with us. He's got a shorter title, Designing Electric Motorcycles for Racing, but I like the longer one, which is rare. Designing electric motorcycles for the Isle of Man Tourist Trophy and the Pikes Peak International Hill Races, the world's most dangerous motorcycle races. This should be cool. Please join me in welcoming Lennon Rodgers to Wednesday Night at the Lab.
For having me. Is the mic working? Okay. All right, so here's a brief outline, and I'll start out with how it all started, which is actually something that is kind of complicated to explain. And then I'll get into the easier stuff, which is the racing, which follows more of an engineering process. So the Isle of Man, the Pikes Peak, and then it evolved into some research that I did as part of the PhD related to distance to empty. And then I'll give you a brief overview of what I've been working on at UW the last 1.5 years. So the easiest way to explain, I guess, where it all started was that I was working as an engineer at the Jet Propulsion Lab in Pasadena, California, in like 2006, 2007, and I had moved out there and I just had a motorcycle and I pretty much bicycled everywhere. And so after biking around LA, you can imagine, for a couple of years, I got smog-induced asthma. And so it kind of started making me thinking. I had a little bit of a conflict, I would say, between my passion of motorcycles and this issue that I had and this awareness of environmental impact. And so I went to the Caltech shop in my evenings, and in 2008 I built this first electric motorcycle. So I called it E-Moto. And the whole idea at the time, I think that everyone was talking about electric vehicles being expensive. And so I wanted to show that they don't have to be expensive. And so I used all components that I sourced online, mainly from China. They were all new, and it cost about $3,000. And so that was really fun. And it was in Popular Mechanics in August of 2008. They did a little article on it. So it's pretty neat. But that's not really totally where it started. It probably started back, even going back to Tom was saying, in Sterling, where I grew up. And I don't know why, but I just always loved motorcycles. And so that's certainly where it started. And then when I turned 18, I bought my first motorcycle, and then I'm a miracle to be alive, the amount of motorcycling that I've done. In all 4 corners of the earth, many different mountain ranges, the Himalayas and the Andes and a bunch of places. And so it's something that I enjoy doing. So that's kind of where it really started. And then probably the merging of my passion for motorcycling engineering came when I started out actually as an art student. And I was in my art class in my freshman year, and I was talking to my classmate, and I was explaining how I'm wrestling with this motorcycle issue that I was having, rebuilding a carburetor or something. And he was basically surprised. And that was the first time I realized, like, maybe I should be an engineer. And so that was probably the second phase of where it all started. But like I said, connecting back to the electric motorcycles really came in 2008. And then when I built this motorcycle, I decided that I was very interested in electric vehicles in general, and so then I decided I wanted to go back for the PhD, because at this time I already had lived out in Boston, got the master's, and actually drove my motorcycle from Boston out to Los Angeles. and was working as an engineer, planned on working in aerospace, but this was really the change for me. And so I decided I wanted to go back and work on the PhD. And it was a unique time with electric vehicles in general. This is the group of people that I got involved with in a good sense. So it was what was called the MIT Electric Vehicle Team. It just started like a year or two before I came back in 2008, 2009. So we were a bunch of mainly guys, but some girls in a shop in the MIT. There's a garage behind the MIT Museum, and we were just building electric cars and electric motorcycles. And one of the things that I was super interested in at the time was fast charging. And so we started doing some research on that. We were working with a company called A123 Systems, which is kind of gone now for the most part. But that was a startup from MIT. And we were using their cells, and we were doing some battery modeling, and we were also doing some technology demonstration, in some ways feasibility. And it was related to the Isle of Man, which I can get into later on. But this is one of the first projects that we worked on with fast charging. And there was a whole paper that I ended up writing on it, so if you're interested, you could check that out. But that kind of evolved, and what we saw in that garage, actually, one weekend we were watching videos, and we saw the videos of Isle of Man, and it was the first time I'd ever heard of it. And I usually tell people, if you haven't heard of the Isle of Man, just do a YouTube search, and you'll see the type of videos and things you'll see. So we saw those videos, if you've done it. The wheelies, the getting off the ground, and all that kind of stuff. And of course, our jaw dropped. And of course, now you hear a little bit of how it all started. Of course, that was a perfect next step for me. So the Isle of Man, actually, I'll tell you a little bit about the history as we go. But 2009 was that first year that they had the electric class. So it was a really unique alignment there. And so I'll tell you a little bit about the race. So the Isle of Man as a race has really been pushing engineering for over 100 years. It's a super interesting history of motorcycle development. Here, just give you an example. This was the motorcycle in 1911, and then 100 years later, that's the motorcycle that we built. And you can just see that evolution. And really, you can track all motorcycle development, or a lot of it, to that race. So just to give you some data to kind of explain and put some numbers behind it. So this is a plot that I put together. On the y-axis is the fastest average speed of the Isle of Man lap, one lap. And then the x-axis are the different years. So it started back in 1907. And you can see, again, there's just a slow incremental increase in fastest average speed. And I have the books on it. It's super fascinating to read it. You can see that each of those data points, well, for the most part, not necessarily each, but in general, these trends are related to different technologies, pneumatic tires, different overhead cams, and things like that. So it's super interesting to see that. And like I said, my initial statement was that really the Isle of Man captures a lot of the motorcycle development over the last 100 years. So I'll give you a quick video here of the Isle of Man course. It's just a fly-through that I put together using Google Earth.
Where is it?
Oh, I'll show that in a second. Yeah, actually it kind of shows it here.
Oh, great.
Yep, so it's a little island between Ireland and England. So it's 37 miles, and the rider starts in one direction, and it goes out. There's a little mountain pass that it passes through. You go up over the mountain there. So yeah, that's just to give you a brief geographical orientation of the race. And here's a brief documentary. So this documentary came out actually right before we were going in 2011. It followed the first 2 years, so 2009, 2010. So unfortunately, we didn't see this before we built our motorcycle. We saw it right before we were going there. And I'll tell you a little bit more about it with time, but it's a really good documentary. This is just the preview from the 2-hour documentary. But I highly recommend it.
The Isle of Man TT, the most famous motorcycle races in the world. For over 100 years, these hills and valleys have echoed to the howls of motorcycles pushed to the limit in search of speed and glory. Until June the 12th, 2009, the day the petrol engines fell silent, but the racing continued on electric bikes. The day of the world's first ever zero emissions Grand Prix, a moment of history.
I thought it would be really boring and really lame, and actually it's turning out to be cool.
Or a moment of blasphemy.
This is the TT. It's recognised throughout the world. They come to see hard men race hard motorbikes, not piss about on battery-powered scrap.
Like it or not, it's happening. Clean, quiet motorcycle racing. Leather-clad maniacs become a force for global good. This is the dream. To build the world's fastest electric motorcycle, take it to the Isle of Man, the toughest, most unforgiving racetrack on the planet, and blow the competition and the skeptics away. In some ways, it's a new dream. The dream of high-tech solutions to global energy problems. The dream of a clean, green world. In other ways, it's a very old dream, one that we all know. The dream of winning.
All right. So yeah, it's very rare that you have like a Hollywoodish kind of engineering documentary, but this is one of them, and it is actually very accurate in terms of following along with these teams and the struggles that they go through. I was mentioning before is that, again, we hadn't seen this, so in some ways you guys have more information in that than we had before going. Pretty much had GPS coordinates, and I'd done a bunch of simulations based on those coordinates and some basic information. But even when we arrived on the island, I mean, I'd never been there. Our rider actually was from the Isle of Man, and he picked me up, and he took me around in his little European car. And I was just like, whoa, what did we get ourselves into kind of feeling when you start going around the course, because it is very curvy, and they're very narrow roads with the walls being very close. Okay, so that, like I said, that gives you a brief overview. And if you want to watch that documentary, it's on YouTube, and I think you can get it various other places. It costs a couple dollars to rent it or to buy it. But I also mentioned before that when we saw that documentary, it really the first 2 years there was I guess the first year there was a very particular type of motor that pretty much all the teams used, and it was really the main one that was available at the time. It was the one that we used, and you'll see in the documentary, and we saw this as we were going, is that every team's motor blew up. And so we were going to this race and we're like, oh no, what did we do? Because we had the same motor. And so a lot of the stuff even that I talk about, that was really the thing that caused us some issues. The only team that didn't have the motor blow up was the team that had the guy that designed the motor, his team. So we were proud to say that we got it to work, and we were one of the few. If you watch the documentary, you'll see why. Okay, so I'm skipping over a lot of details, but like I mentioned before, it was a very unique time. It was a time where we started to try to, I started finding a team. I mentioned the MIT EV team, and then I started trying to get sponsors and this kind of stuff. It was really a grassroots effort. And through various connections, I was connected with BMW in Munich. And again, this unique time where BMW in Munich was willing to talk to me, I'd built one electric motorcycle, but it was so new to them that it was that new. And so I went to Munich and gave a talk, and I met all the people in racing, and it was super interesting, especially now that you know my background. I had to sign NDAs, and I saw all of their projects they were working on. It was awesome. And pretty much at the end, they were like, yeah, we'll commit to give you a rolling chassis. It was their S1000RR, which was just coming out that year, so the timing was very good for that. And then similarly with A123, there was the professor, Yetming Cheng, who started that company, and he just so happened to be a motorcycle enthusiast. And so that was another really good alignment. And so they sponsored and donated batteries. We worked with them to make them custom to what we needed in terms of the size. So those are the two main industry partners that we had. I'll just give you a brief overview, just fly through it in terms of the design process. It seems very clean here, and for the most part it was. But I'll try to interject and explain some of the complexities mainly related to those motors that I talked about. So early on, it was systems engineering. Then I'll go through a little bit of the subsystem design, some of the prototyping, the incremental testing, and then the racing and then model validation. So the systems engineering, those are the GPS coordinates pretty much that I mentioned at the beginning. That's pretty much all we had. And so we were trying to estimate how much energy we would need to get around the course. It seems, again, very easy now, but at the time, we had no idea. Was it 5 kilowatt hours? Was it 6 kilowatt hours? No clue. There was no information available online. There was no published papers. So it really came down to our own calculations using those coordinates and some of the assumptions. And the second question was, will the batteries fit? And so we knew teams had gone, so we knew it was somewhat feasible, but those were things that we practically had to figure out ourselves. And then the second more systems engineering type effort was related to performance prediction, like, okay, maybe you could have enough energy, but how fast would you go? Would it be competitive? And things like that. So this is just some of the results from some of the simulations. So the basic hypothesis that we had was that the battery energy we needed was in between a best and worst case scenario. So this plot just shows battery energy versus distance. And so these are some simulations that we ran. And I guess the details really don't matter, but the bottom line was that we had a basic idea of how much energy we thought we might need. So that's what we built our battery pack around. I'll get back to this plot at the end. And then we just had various simulations we made. So this is just one plot with power versus speed and trying to understand the different trade-offs we could make in the design and how we would perform. So just kind of cruising on to prototyping and fabrication. So we used a lot of prototyping tools available at MIT, and it's kind of neat now jumping, I'll talk about at the end at UW. I mean, this is really what we want to enable students to be able to do, is just to prototype to build some of their designs. And so this is just some examples. This is the structure that housed the batteries in the motor. And so on the lower right is that assembly on a jig, and we were welding it. And then there's some cardboard mock-ups in the upper right. But there's a lot of prototyping using water jets, laser cutters, things like that. The other thing is that we were taking a gas engine out of a motorcycle, so we tried to preserve the structural loops. So here's the stock motorcycle, the S1000, and then you remove the engine. That's kind of the next picture. And then the lower one is the one with all of our batteries and our motor on it. And so we tried to preserve that structural mechanical loop that's kind of drawn in green there. And we had a couple things that made us lose some sleep. One part was that there is a part in the course where the motorcycles typically get airborne. And so there's this thing called chain whip where the wheel will start to slow down and then it hits the pavement and then there's a huge shock wave through the system. And a lot of motorcycles have little features to help with that. We were building our own, so we had to figure that out ourselves. And so that was this is a finite element analysis there showing the chain whip. I'll show you in the video. We did get air, not much air, but we did get air at that spot. And the guy on our team that had done all these simulations, it was kind of, he wanted to get a picture at that spot, so he was very proud of this picture, which I'll show you. Because he designed this thing and he said it's not going to fail at that point, and he was right. Okay, so we had a lot of sensors and microcontrollers for real-time monitoring. So that was one of the unique things in our approach in general. The racing, the Isle of Man, or racing in general, it's not a very open culture. A lot of academics don't really go into that space. And part of that is that they don't share information. And so a lot of the rules said you can't have GPS, you can't have sensors, you can't be logging things, and there were a lot of rules. We pretty much just ignored a lot of those until right before scrutineering, which is that process right before you're going to go out on the course. And we just let them know like moments before. And then we're like, just so you know, we kind of have a lot of that stuff that you told us not to have. We wanted to be honest, and they're like, oh, it's fine, go ahead. So for that, it's kind of nice because we were the first people that I know of to ever publish any information about the race in terms of this level of engineering detail. So it was neat. And I think it has to do with that the electric class was new. Again, that's probably going to change in 10 years. So just to give you an idea for some of the sensors that we had a battery, the current, the voltage, state of charge, temperature, a lot of fault detection. The motors had current sensors and temperature sensors. The vehicle, we had speed and acceleration and GPS. And we had a display for the rider. And it actually was wireless, but we could only read it within about a mile. And an interesting story about the display with the rider is that we initially planned on having some kind of fancy display that had all this kind of information. And when we showed the rider and was talking to him beforehand, he pretty much says he doesn't want any information. He's not going to look at the monitor, the display at all. And he just said he pretty much just wants to go full throttle the entire time. So that was kind of his riding strategy. And even if you know electric vehicles, you can tune a lot of the stuff in the software. And we pretty much made it so he could just go full throttle the entire time because he didn't want to have to think about anything besides looking straight ahead. So we did have a display, and it had some engineering features to it, blinking LEDs for us to diagnose things, but it was very simple. The next thing that I want to talk about, just some of the incremental testing. This is something that I think all engineers really know about, is that the cost of errors, which is shown on the y-axis, really increases as you approach whatever you're building this thing for. So in our case, it was the race. So we tried to have a very iterative design process where we stayed down in this very low-cost spreadsheet sketches, low-cost prototypes phase. But at a certain point, you find yourself in this scenario here, which is where you're way up the curve, and you're not going to be able to make design changes at this point. It's very, very difficult to re-weld things and make any changes. So this is the motorcycle on a dyno, a chassis dynamometer out in or I guess it was just south of Boston. And this is just to show, usually when I talk about this with students, it's kind of, this is an example of why you want to stay down in this low cost, easy, everything's fun and simple phase of life. When you get to this phase, you want to have done all your homework and you don't want to be able to make changes. And we didn't have to make any changes, again, besides this motor issue. So I'll show you a brief video of some of the incremental testing, and it really kind of goes through all the races to the actual final race. One thing I didn't know about racing is that there's much more than just the race, the final race. There's a lot of qualifying races. So it's a bit of survival to actually make it to the race, which is a lot different than like 5K runs that I've done, which is you show up and you run the race and it's like, yay, I'm done. Actually, most of the effort is before the race and you're exhausted. And if you survive, you actually then get to race at the very end. And the Pikes Peak was actually potentially worse in some ways. But that said, it's something that we were really proud of because we actually, we may have been the only team that year, there may have been one other one, that actually we finished the 2 qualifying races and then the third, the actual race. And so that's what's shown in this video here towards the end. So these are our batteries, just doing a lot of benchtop testing. And we spent a lot of time at the chassis dynamometer. We had to make a lot of friends with, in this case, the chassis dynamometer. This is at a Harley dealership in Boston. And this is in a hallway at MIT, and everything was just, nothing was welded at that point, but it was very low speed. And then we put it in a wind tunnel to try to get some of the coefficients. And we took it to a test for testing up at a track in New Hampshire. That was probably one of the funnest things about it, was just all the people you meet along the way. And we were spending time with these motorcyclists that have track days and things like that. And they were super excited to see the technology and super friendly. And I'd never raced on a track before. So the motorcycle was put in a crate and was shipped, actually in an airplane to the Isle of Man. And because of various regulations, we had to totally rebuild it. And so we have to go back, test it on the dynamometer again, do slow speed tests, do high speed tests. And this is the point where we told them about the data and that we'd broken the rules.
All right, Alan!
So these are the qualifying races.
All right, good job.
2 in a row.
Yeah.
So he's saying 2 in a row because he was amazed that we had done the 2 qualifying races. And so we had to rebuild the motors in between the second qualifying race and the final race. And it was a super intense discussion about risk mitigation, among many other things, of why we decided to do that. We didn't have to, but in the end, I'm really glad we did. So this is the starting line. There's grandstands, but for the most part, you just don't see the rider. He goes out in one direction, and then you've got an app that you can track him on. But we didn't see this. This is from a camera crew, a TV crew that was taking this. We just pretty much sit and wait. So there are various speed traps throughout the course, and it will then update the app, and you can see. So obviously everyone's huddled in a tent and seeing the 4 or 5 different spots where they, okay, this is the spot where they got air, a few millimeters. So Alan was the name of our rider, and that's him there, and this is our team. All right, so our average speed was 128 kilometers an hour. When I've given a talk in Boston, it's much easier. Madison's a little harder because I say, well, that doesn't sound like that fast, but imagine going through downtown Boston around all the curves at that speed. And people are like, whoa. So that, again, Madison, I don't know the equivalent because every road's pretty, I mean, you could go this fast anywhere. So we were the fastest rookie team, and then we were the 3rd place team. We were the 4th place motorcycle. And I published a paper on it in 2012 if you want to read about a lot of what I've been talking about today. So the final thing in what is also talked in the paper is to go back and look at some of our assumptions and try to use some of that data to understand if our models were correct. And so this is the same plot that I showed at the beginning, which is battery energy versus distance. This is when we were trying to figure out how much battery energy we needed. Long story short, the racing data confirmed the hypothesis. The energy was in between those best and worst case scenarios. So it was good, and we did not run out of energy. This is just an example of some of the other data. We had a lot of data. But as I mentioned, it's one of the neat parts about it, I think, is that we have all this data about this very historic race. Okay, so now on to the Pikes Peak race. There was a few years in between. I had lived in Switzerland, as Tom mentioned, for a while, and then I had gone back to MIT as a research scientist. But in the back of my head, I always thought, oh, the Pikes Peak would be a fun race to do. Mainly because there were just a few 100-year-old races. So Isle of Man is one, Pikes Peak is another, Indy 500 is another one, and then the Mount Washington Hill climb is another one that's sometimes given credit, and maybe there's some other ones, but there aren't that many. And so the Pikes Peak was another one of interest. The other reason is that it's such a different type of race. So it's a mountainous course, and so it's much more about having torque and power than necessarily energy. So it's considered the 4th oldest motorsport event, and here are just some of the pictures that I got online about the historic perspective of the race. And here's a video showing the course. So it kind of snakes along the road there. And there are also these little marking milestones with really awful names like Devil's Playground, which, you know, can't be a good thing. And the finish is at the summit. So somewhat similar to the Isle of Man. I mean, I didn't really know much about the race. I had, like a lot of us, in 1980-something, our family got in the minivan and drove from Illinois out to Pikes Peak, and we drove up, put the bumper sticker on. That was pretty much the last time I had been there. But we did a lot of the same type of things, which I'll go into. But just to compare the two races, so they were started, around the same time. The Pikes Peak is much shorter, but it's much steeper, as you can imagine. So much larger elevation gain. But it has about the same number of turns. And I think the interesting distinction here is that The Isle of Man is really largely about energy. You could run out of energy. That's a real issue. Pikes Peak, you're probably not going to run out of energy, but your motors might overheat, and it's really about power and torque and that kind of stuff. And if those of you that have followed the race, that's why EVs are kind of dominating this race. They're not quite dominating the Isle of Man yet, and it kind of has to do with that, that reality. So I'm going to just go through very briefly. We followed a very similar process. Maybe I was a little bit older and wiser, but it was the same idea. So we wanted to go fast. We didn't want to run out of energy. And we wanted to be able to understand and improve what we were building. So very similar to before, we generated some models. We tried to simulate various aspects of the course. These are similar types of plots. In terms of simulations and trade-offs, one of the things that we wanted to do was figure out where we should focus our energies in terms of, should we have a huge motor? Should we try to have a light motorcycle? So we did some simulations, and it really showed early on, which is somewhat intuitive, that you just want a very light motorcycle. That's because you have such a huge elevation gain. So what this plot shows is the reduction in energy, how much energy you could save basically by reducing various parameters. In this case, it's drag coefficient, mass, and rolling resistance. And mass is red, so it's like if you can reduce your mass, you're really going to save a lot of energy going up the mountain. So the times had changed, even in the few years between Isle of Man and Pikes Peak. And the big difference is now we could actually go to a local store and buy an electric motorcycle. That wasn't the case. So we worked with a company called Zero Motorcycles. It was really fun to work with them, similar to BMW and A123 in the past. So what we did is we pretty much took their lightest motorcycle frame and then took their biggest electric motor and then combined the two. So kind of the biggest of the motors, smallest of the bikes, and merged them together. And that was our race bike. And this was a lot different because we actually had we had like 4 international partners. And so the Isle of Man was much more a bunch of guys in a garage at MIT. This one was a lot more about collaborations and working with people, which is really a good experience to have. And so there was a team from Japan and the UK and others, so we all kind of contributed to the motorcycle. So here's a summary of upgrades. We reduced the mass by adding magnesium wheels. We removed, obviously, everything that we could that wasn't essential. There was a motor and a controller upgrade that I mentioned. We kind of took the largest of those from their product line. And there was a custom battery. There was race front and rear suspension, and we changed from a belt to a chain drive. And there was a new fairing, and we lowered the suspension. So the result was a 16% reduction in mass and a 51% increase in torque and power. So it was really good. And here is just to show various specs on the motorcycle. So the stock FXS, which they actually have a 2018 version. You can go buy one now if you'd like. This is about what you'll still get, which is shown in the stock column. And then the next column is the one that we modified. And so that shows the change of 16% reduction in weight and then a 51% increase in torque. So the final thing is just similar to the Isle of Man. We're engineers, so we really want to understand this vehicle, and we have a lot of sensors, and that was the case here. So we knew the ambient temperature, the pressure, the humidity, motor temperature, voltage, current, all the vehicle stuff that I mentioned before. Heart rate was new, so we had a heart rate sensor, which is interesting. We had a lot of other sensors, some of them failed, but those were kind of the main sensors that we had on the motorcycle. So that's a brief overview of the Pikes Peak. This is a video showing a lot of the process, similar to the Isle of Man video that I showed, all the way to the finish line again. So this is at a testing track out in Western Massachusetts. And this is in Western Massachusetts. So we all converged at a motel in Colorado. And you'll see a lot of Japanese, because this was a Japanese filming crew that was following our rider, who was also, he's not an engineer, but he was extremely technical. So these are the practices that I talked about, extremely grueling. 1 hour, 2 hours sleep, best case, for 5-6 days. And you'll recognize some of the same faces. So that was my friend Mark, who was also a grad student. But that student there was from Sweden, the other one. So this is up, I think, at like 10 or 11,000 feet. And this is the survival part. And this, a lot of things you're trying to fix, and you'll notice here he has a backpack on, I think, in this one. And our data collection system's not working, so okay, throw this laptop on and put it in a backpack and go. So that's kind of the phase we're in right now. Working out kinks, we had chargers blow up, and I'm driving up. Actually, I don't know if you guys know Kilocycle, the drag racing bike. I know that guy, and so he lives in Denver, so I'm like, can I borrow your charger? Yes, okay, I had to drive to his house and pick it up. So this is the actual race. This just shows the sensor, so here's his heart rate, and it's just an overload of information here. But here's RPMs, this is kilometers per hour, and there's a lot of temperature data on the bottom. And here's a little map of the course actually in the upper right-hand corner. There's, like I said, there's so much information packed in there. So that's the finish line at the top. And so this is the team for Pikes Peak. And these were all the partners. So a funny story, and I talked about at the beginning that I like to motorcycle. I'm a motorcyclist. I've done a lot of motorcycling. Well, it's, in all honesty, when I first heard of the Isle of Man, I thought, oh, maybe I could ride in the Isle of Man race. Well, a good story to just totally realize how silly that is. When we were at the Isle of Man, we were doing some testing up on the north side of the island. I showed you some of those videos. That was me kind of flying by. But you could hear, Mark, and the other guy, and I were the test drivers, and then we had our actual rider that would ride for the race. So Mark and I were testing up the north side of the island. You could hear us off in the distance testing, so like going around all the turns. So that's us. That's a non-professional rider. So the rider himself, he gets on the bike. It's you could hear it. So and it was the same thing with Pikes Peak. These guys are amazing. The way that they can, you could see that in the video. It's a whole different level to be able to ride a machine like that. So I'm nowhere near that. So these were the results of the Pikes Peak. So we were the fastest university team. We were the second place motorcycle. We were beat by what was originally called Bramo, but then they were bought out by Polaris. So they just had an amazing machine there that was super impressive. The max speed was 92 miles an hour. The average speed was 67. And then we used about 4.2 kilowatt hours. So to put that in perspective, that's about a Coke can worth of gasoline. Or a washer and dryer load-ish kind of thing, roughly, gives you an idea. So not a lot to be able to do that. I'm actually in the midst of writing a paper right now on this effort, the Pikes Peak, for the SAE conference in Detroit coming up here. So I don't have a lot of digested results to show, but just as an example, this is just an experiment, as an example of some of the data that we have. And really what we wanted to understand is how could we have gone faster? Was it the motors limiting us? Was it the rider? Was it his heart rate? Was it other things? So this looks at temperature, and this is distance. And actually, so you could see that we were quite below our temperature limits. So anyway, that's foreshadowing what I'm writing about in the paper, but it's something that I'm interested in digging into. So I think I've actually never explained kind of the chronology from that original motorcycle in Pasadena all the way up till now, but you can kind of see that the first one was pretty much all I could do by myself. I mean, it was that I was in a garage at Caltech building this electric motorcycle, and it was fun and cool, but the real fun gets into the team efforts. And so that was the thing that I really learned. I mean, I was working at JPL as an engineer. I was building big, complex systems, so I knew the team was essential. But all the stories I described, I mean, it's much grittier. And when you're with teams, with the team and working in an engineering team, it's really rewarding. It's really fun to do things that there's no way on the planet I could have ever done myself. And that was definitely the case with these two races. So here, like I mentioned, I showed you pictures before. This is the team. I don't know why, but it ends up always starting very large, and kind of by the end, there's about this number of people that are in on it for the last 6 months or so leading up to the race. And very similar with Pikes Peak. But yeah, it's really neat to see it, and I think those that have worked on complex things, even in the sciences and in engineering, we're almost all orthogonal axes with our own strengths, and it just works together, and it's really magical to have that experience, those kind of experiences. Okay, well, the next part is related to really what happened afterwards, and it kind of gets back to the individual work again, because a PhD, you can't get a PhD on motorcycle racing, and it actually has to be very individually focused research work. So that's pretty much what I did for a couple years after that. Now I'm going back to the Isle of Man. In reality, I had to say, well, okay, I spent a lot of time on that. How can I leverage some of that and then work towards some interesting research question? So I started looking at this, the topic of distance to empty, and this is like 2011. It was right when we got back. This just to give you an idea, and like I have a whole talk on this. Obviously, I had a whole thesis defense on this topic. But to introduce you to the concept, this is the Nissan Leaf electric car, and that number in the lower right-hand corner, that's distance to empty. So you're trying to predict how far you can go on a charge. And I don't think I have to go into much explanation that you can see that there's a lot of connection between the work in terms of trying to predict how much energy we needed on the Isle of Man to something like distance to empty. So the premise of the research is really this issue that a lot of algorithms, especially at this time, they're trying to estimate how much farther you can go, but they're only using past information. And so that's what's shown here. This is a Tesla Model S. You're in the present, you've got your past driving information, but how do you predict the future? And so this is work, again, that was kind of finished in 2013. There's been a lot of work in this area since then. But this was the idea at the time, and this is one of the algorithms that I developed. So conventional methods, as I mentioned, only use past driving information. And what I worked on was an algorithm that used past information plus estimates of the future driving conditions to try to improve the estimate. And so that was pretty much that research. And there's a paper that I wrote on it if you're interested in it. As part of this effort, I went back to BMW and got more involved with the automotive group. So it was a unique opportunity that it was pre-production of the i3. And they had released this car. Has anyone ever seen this car? It's called the Active-E. Yeah, so it was released 2011, 12, sometime around that. When I came along, what BMW had was terabytes of data. And they were interested in working with me to try to analyze some of the data. And so I looked at the data in 700 cities, in 700 vehicles across the world in 7 cities, only in the US are the ones I focused on. And it was over 100,000 trips to date. So it was actually 2 of us at MIT, and then they had a data person at BMW in Germany, and the 3 of us worked on it. And we wrote this paper in 2014. Just to give you an example of some of the results, in general, I was using the results to improve this algorithm that I talked about before of trying to understand range estimation. But as an example, this is a distribution of change in energy between subsequent drive charge events. So this is pretty much like you charge your car, you go drive it, however long you do that, you come back, you plug it in, charge it again. What I was trying to understand is, well, how much change in energy is there between one drive that you did that charge cycle and then another time? Because if they're very steady, it's actually very easy to predict range, right? You just use the pass, like what most algorithms do. But the results here using that BMW data showed that there was a 15% probability that the energy use would change by 30% or more. And so that's when the algorithms start getting screwed up, is when you have those kind of significant changes. And it has to do with auxiliary energy use and a bunch of things that I dove into with the paper. So that's kind of it for distance empty. I'm happy to answer any questions, but that's how I ended up working on EVs for some of the PhD research. Finally, I just wanted to give you an idea for what's going on here at UW, because that's what really I do every day now. I don't work on motorcycles much anymore. So some of the information about UW, I was at MIT as a research scientist, but kind of during that process you saw, and it really stems way back as an art student, it really was this desire for hands-on learning, making, building. I mean, that was the way that I've always been. And when I was at MIT, I did these projects, and through that process, I met all the shops. I got to know all of them. I became trained with all the shops. And there was a unique opportunity to create a new makerspace at MIT at that time. So I helped create that one. And then my advisor was saying, hey, we have a collaboration with Singapore. Will you go over there and create a makerspace there? So I went and did that. And then when I graduated with the PhD, very similar, another advisor of mine said, hey, we're trying to start this university in Russia. Would you go over and help them create a makerspace there too? I mean, they call it different things, Fab Lab. In Russia, they call it Masterskaya. But so that's kind of the precursor. But so when I saw the job posting at UW, that was super appealing. Partly that I love that topic, and also partly married now, 2 kids, and wanted to come back to the Midwest. And we were super interested in Madison. So that's how I ended up back here about a year and a half ago. And the main thing that I was asked to do initially was to create this makerspace, which was all started in 2015 with a donation by the Grainger Engineering Foundation. So that was kind of the right part, which I'll talk a little bit about. But I also help oversee some of the machine shop, just more from the academic side. And I could get more into that in a little bit. But just to give you a little bit of layout of the shops at UW in terms of in the College of Engineering. So Team Lab is more of the traditional machine shop. It used to be called Student Shop. There's 8 full-time staff. Makerspace has 3 full-time staff. There's a lot of student staff that run the shops, and so that's also part of the effort that I've been working on. So we have about 63 student staff total, and there's about 24,000 square feet. So it's a huge opportunity for students to work on projects. Here's a little bit of the chronology, and I alluded to part of it, is that in the early 90s, and I should mention, this is all told to me orally by the people that have been around, so you may have more information. But I was kind of curious about what's the history of shops, because they're all quite different. At MIT, there's a whole history. And each place kind of has a history of how they run their shops on campuses. So in the early 90s, I was told that the engineering shops started to consolidate. In 2008, they established a formalized training program, which is extremely impressive. It was one of the aspects of the job when I came and toured. I was like, wow, this is extremely impressive what they have in terms of formal training that's available for students. 2015 was the gift by David Grainger. 2016, they started renovating. That's when I came and was interviewing, and I saw the library with all the chairs flipped over, and they were starting to gut it out on the first floor of Wendt. And then I joined in the summer, and then we opened in September of 2017. And so as I mentioned, Team Lab, that's the more traditional shop. They also have fee-for-service, but it's mainly around metal and woodwork. So that's the mills, the lathes, the saws, and this kind of stuff, welding. And that's the website. And then the Makerspace is the thing that's the newest on campus in terms of capabilities and culture. It's more about do-it-yourself projects for students. I think the motorcycle is probably an extreme example, but it is an example. It's more about 3D printers, 3D scanners, laser cutters, and all those pieces of equipment. And then there's a website there if you want to check it out. But there are just a few points I just want to make briefly about the Makerspace, and I'd be curious about your thoughts or even afterwards any of the feedback you have. But one of the main themes, and it's something that I greatly benefited from, is having a space that is for students. You know, it's really students are running this facility. So the Makerspace is largely student run, and so we have about 30 student staff, and here's just pictures of some of them. And it's just a really good opportunity for them to have a very long runway, a real great opportunity for development and growth. And as part of that, they run workshops. So pretty much every other night we have some kind of workshop in the Makerspace. And it's really about peer learning for the most part. These are students teaching other students. And it's also about interdisciplinary activity. So here's just some screenshots from various workshops that we've had, from virtual reality to 3D printing to microcontrollers, to finite element analysis. So there's a lot of different topics. We had, I think in the last spring semester, we had about 75 of them, and I'll show you some of the data from that. But here are some just pictures from events in the space. This is just the Makerspace. So like I said, the first part is kind of the student-focused aspect to it, and really the student empowerment and peer learning and all the things that come along with that. The second part is that it's really more than a traditional Makerspace. So I would say a traditional Makerspace is up in the large physical, macro physical space. So these are the routers, the drill presses, function generators, and other things. We're also super interested in the virtual space, so we have a lot of virtual reality. And then we're also interested in the microspace in terms of some of the tools we have, like a microfluidics printer. The third point is that really the interdisciplinary aspect of it. And so we've been working a lot on creating various interdisciplinary programs and supporting programs. So it really starts from high school, and we support some of the high school programs that exist already. But it goes all the way up through capstone courses and to a master's degree. So we've spent a lot of time creating this master's degree, which is going to start in 2020. And it's a collaboration with the College of Engineering, iSchool, School of Business, School of Human Ecology, and I don't know if I said the art department. The art department's in there, and the College of Engineering. So it's these five. And it's really exciting, and it's really around this idea of design and innovation, which is kind of an overused term, but I think how we mean it is just really generating new products and services that solve true human needs. And this may seem like a little bit of a, like, wow, how did you get from motorcycles? But I kind of skipped over my whole involvement at MIT in product design, and those are a lot of the courses that I taught. And so that's very similar of what we're doing here. And this is a course that we prototyped with the School of Human Ecology this past summer, and we worked on the theme of farmers market. So the students went out through the farmers market and looked for various product opportunities. And just another point, it's really my final one, is just some of the data that we've collected, and it really has to relate to the mission statement. And this is a whole other presentation that I'm not going to go into. I just wanted to highlight it for you guys to show some more relevant, more recent projects that I'm working on. But with the Makerspace, we had this opportunity that the College of Engineering had a shop for many years, and I showed you some of their chronology. And then all of a sudden, there's a step input of this new Makerspace, which has some of the facets that I talked about. But we were curious, how did that impact things? So a couple of the research questions we looked at, and we presented a paper on it out at Stanford just this past summer. We looked at these two things. So we said, how did this Makerspace impact the number of females and targeted minorities using engineering shop facilities? And then the second part was the interdisciplinary activity. So I'm not going to go into the details, but the bottom line is that we looked at the data. So we looked at user data from when the Makerspace was added, and we compared that to before, when there was just a shop, just a machine shop. So it was kind of those two together. And the bottom line is that in terms of females and minorities, we saw a 2.9x increase total of total people going into the shop facilities, including the Makerspace. But we saw a 3.9x increase in females and a 3.7x increase in minorities. That was over a 9-month period. And so similar with formal training, that was people coming into the door. This is actually some of the formal training. So the bottom line is we're seeing some increases, which is good. That's what we wanted to see. The second and final point is really about interdisciplinary activity. So the point here is that if with this Makerspace, what we didn't want to happen is that mechanical engineers come in and just learn about mechanical engineering. We really wanted a space where mechanical engineers learn about other disciplines, where other schools and colleges can come in and learn about other disciplines. So here's just, again, some of the data. So after the Makerspace was added, there was an increase in departmental diversity within the College of Engineering. So before the Makerspace was added, we saw most dominantly mechanical engineers going into the shop, that's what I am, and that's most traditionally the case. And then after the Makerspace was added, we saw an increase, which is shown in green, of people from electrical and computer engineering, computer science, and other engineering departments. And then the final thing was this matrix that we developed, and we talk about it all in the paper that I wrote if you're interested. I actually brought a couple copies. But it goes to that thing that I was mentioning before, is that our mechanical engineers coming in and learning about mechanical engineering topics. So that's kind of the 2 row columns of the matrix. Our mechanical engineers coming in and learning about mechanical engineering. And if they are, we would see 1 down the diagonals here. And if you see a lot of off-diagonal values, that indicates that there's a lot of interdisciplinary activity, which is what we want. And so the bottom line is that on average, 70% of those that attended the workshops that we had learned skills outside their major. So that was good. So that's pretty much all I have. And thank you very much for coming, and I'd be happy to answer any questions you might have. Yep, go for it.
On the video showing one of the races, the heart rate of the rider was 185 at the time.
Yeah.
Is that from the physical activity of riding or from adrenaline?
That's a good question. Okay, so we did look at the heart rate. It pretty much plateaued out. So I do have a plot. I don't think I have it here, but it pretty much just like went up and it flattened out at whatever around that value. There are a lot of papers on that topic. So related to the paper I'm working on now, I looked up and read a lot of those. So I think it's kind of related. I mean, I think it was definitely adrenaline. He has like a kind of a ritual beforehand. He gets himself all pumped up. But I think it was also very physically hard. I mean, he's worn out. It's very physical. You saw in some of those videos that, I mean, it's actual physical activity. So, yeah. Yep.
Back to the Isle of Man, how large was the motor? What was the capacity or capability of that motor, A123? And how much consumption of battery was using? How much did you have left?
Oh, right. Okay, so the question is, what were the capabilities of the motor and the battery, kind of the drivetrain, and how much energy did we use and have left over? So the motors were 16 kilowatts each, continuous. I can't remember the current. It's like a few hundred amps. And we pretty much maxed them out. I mean, they were at their thermal limit. And in terms of the batteries, it was very similar. We pretty much maxed them out. And in terms of energy use, we used, we had on board 11 point something kilowatt hours, and we used like 9 kilowatt hours, something like that. So we had a little to spare. But it was really the motors were the biggest limit in our case. And how those motors fail, and if you watch the documentary, is that they're all it's all floating on this resin that has a certain melting temperature. And once you hit that melting temperature, the whole rotor the whole motor explodes. It just slides and hits the magnets. So yeah, we were just kind of like on the edge of that all the time. Yep.
So when I think of electric motors, using electric motors to move things, I think of railroad locomotives where the motors are in the trucks, the wheels of the locomotive. I now see electric bikes where the motors appear to be in the wheel hubs. And when I watch the Tour de France, there's talk about riders who cheat by putting small motors in the hubs. And it looked to me like you guys put the motor up in the chassis.
Yeah.
The question is, why can't you put the electric motors, in the hubs of the wheel?
No, I mean, we thought about all that stuff early on. I think the easy answer, I mean, is that at that time, and still is the case, I mean, to get 32 kilowatt motor, it has to spin pretty fast. So it's a little bit to do with RPM. So I don't know if I repeated the question, but the question is kind of like, why don't you have hub motors, different motor architectures? Why did we have the one that we have? So that's part of it. So within hub motors, so in the wheel, they can't spin as fast because you're going just one-to-one with the wheel. So you don't have that mechanical advantage either. is part of the issue, and it can't spin as fast. So yeah, I don't know of any that you could get 32 kilowatts. And now if you were to want to go back and be competitive, you would need even more. So that's one of the issues. The other, the common issue is what's called unsprung weight. So if you have weight that's on the wheels, it's just considered unsprung weight, and so it's just a different type of riding dynamic, and so you want everything kind of on the suspension. So that would be another reason. But it is interesting with bikes, bicycles, because now it seems like with the Bosch system, everything's kind of going down into the crank, and that makes a lot of sense to me after I've blown up. I didn't talk about this. There was a whole other project I didn't talk about, which is where students built an electric bike. This was in between the Isle of Man, I think, and Pikes Peak. And they rode like 300 miles on this bike. But anyway, we blew up a lot of hub motors in that process. And it was mainly because, again, you just can't get the juice out of them because they can't spin fast enough. Yep.
Yeah, so in your preparation for Isle of Man, you spoke at some length about the challenge of modeling the energy consumption you were going to need.
Yep.
Right? So my question is, since you're partnering with BMW and they compete in a race with petrol motorcycles, would it have been possible to use information about weight of bike, weight of rider, average lap time, and fuel consumed during the average lap to understand what the energy demand was going to be?
Yeah, so the question is kind of like with modeling, I think if I understand, was there more information available, or what other inputs could you use to models to make some pretty advanced, sophisticated modeling?
Yeah, what did you know about what gasoline motorcycles consume?
Not much, yeah. Like none of us had really done anything in racing, and I kind of mentioned at the beginning is that racing's not an environment for sharing information. So here are just a group of academic guys coming up trying to do this, and there's not a lot of information out there. And BMW didn't offer anything up when we went there. I mean, and then there was the head of racing right there at the table. It's just that's kind of the environment, I think, in some ways. And they were very open and interested in collaborating at the same time. They just kind of wanted to see what would happen. It was early enough that they weren't all into it at that point. Interestingly, if you do a Google search, you'll find an electric S1000 that came out much, much later on. And that's kind of how long, I guess, it took for them. They made a prototype and it came out. It was just a couple years ago. It looks a lot like our motorcycle, but I mean, a lot nicer because it has their finishes on it. But they eventually did come out with an electric motorcycle with the S1000, which is kind of interesting. But at the time, and I think it's still the case, is that most people in racing think that motocross, off-road, that's kind of where electric could be more interesting. So there has some attention into that in terms of motocross. And that was kind of BMW's, that's the sense I got from them. But okay, so in terms of the modeling, that really all we had was GPS, and we had like motorcycle dynamics books and things like that, but there wasn't a lot of information available. With Pikes Peak, we are doing some interesting, and I'm working on it kind of right now. It mainly has to do with some more pragmatic issues, which are like, what sprocket ratio do you use? And it's these kind of details that are practical and very useful. And so there's some modeling that is a little bit more sophisticated, but in general, we find that we're kind of coming up more with like heuristics. It's kind of trench level warfare. And so it's not, you just need the general heuristic and kind of head in that direction versus very detailed, super detailed modeling. But we had a pretty good model. You could read that paper if you want on it, and it gets into more details of the modeling. But it was mainly on the drivetrain. The vehicle dynamics not as much, and the course not as much. It was mainly on the drivetrain modeling. Yep, in the way back.
I wonder if the Nelson School of Environmental Studies has shown an interest in life cycle assessment as a dependent variable for your master's degree program?
So like you kind of do the design side of things?
Right.
No, we haven't gotten to that depth in terms of exactly the curriculum of it. We have a basic outline for with the electives and things like that, but it's certainly a good topic. That's the topic I mentioned, the product design community I was part of at MIT. That was a big topic. The question was about life cycle analysis and including that in the master's degree. Yep.
There's been a fair amount written about the decline in our society of DIY and
the ability to tinker and that sort of thing. Cars are all sealed now, you can't do your own maintenance, et cetera. Do you see that changing or reversing that trend with the makerspaces and other initiatives?
Yes, that is a super interesting question. So the question is, and I mean, I hear this all the time, used to be that you could work on cars, and you used to see a lot of students, I hear this here, is that a lot of students used to grow up, engineering students would grow up on a farm, they would learn how to work on machinery, and then they'd come to UW and be these amazing hands-on engineers, and like, where did they go? Yeah, I think it's super promising with the maker movement. I think it's certainly a big aspect is at home, I think, still. But a lot of kids are getting it in high school. I mean, I was kind of on that edge of I still had shop, and then the CAD came along and all this weird kind of stuff. But now I know a lot of kids they have access to fab labs and makerspaces in high schools. I'm super optimistic, and I think that you will also be optimistic if you go over to the makerspace and just see the amount of investment that's going into it. But I think it's just starting. I mean, even that International Symposium of Academic Makerspaces, which is the global consortium of people in academic environments looking at this, it's only been going for 4 years. But no, I'm super optimistic, especially with the amount of information that students can find online. The final thing I want to say is that I do think there's kind of a difference between the tinker and the maker, which is, it kind of has a general term, versus I'm more on the engineering side, so I'm super passionate about engineering principles and that kind of stuff. So I think there is kind of that, there's a huge difference there. But so everything I talk about is kind of the engineering principles. I'm super optimistic about that. The maker, which kind of overlays with crafts and other things, that's kind of different. I'm not as active in that space. But in terms of using tools and tinkering and that kind of stuff for students to learn about engineering principles, I'm super, super optimistic, and that's kind of why I came here. Yep, in the middle there.
Early on, you mentioned or showed that there were 250 people that had died.
Yep.
Ironman. Is this considered one of the most dangerous sports going? And if so, you haven't once mentioned anything about safety.
Yeah, the Isle of Man. And so the question is about the number of deaths at the race. Yeah, on average, there were 2 a year, I think. And so, yeah, it's kind of so safety was like number one for sure. I mean, that's what we lost a lot of sleep over. Probably the most real aspect of it is that interface with the rider. You see. And that trust, it's like engineering. He was trusting us to build a machine that was safe enough for him to ride. And I remember I was actually staying at his house a couple days before the race, and I saw his dog tags laying on the table, and that was kind of like sinking at home there, just imagining, the safety implications. So safety is huge, I would say, for us. There's no one that's died in the electric class, partly because the speeds are a little bit slower. But yeah, I mean, safety is a huge aspect of the race in general. I don't know if I answered the question. I mean, is there anything? So I'd be like, yes to that fact that you stated about the number of people died. Yes, in the sense that safety was something on our mind all the time. Besides going back to good risk mitigation and considering risk and all this kind of stuff, incremental testing, then some of the stuff I showed, we did everything we could, and we felt like it was a super safe motorcycle we could build. Yep.
So you said that a lot of the motors exploded or they exploded?
Yep.
So is that a safety risk for the rider?
It wouldn't lock up the motor from what we saw. Even when we had a motor, we did have a motor explode on the dyno. And I should actually even kind of relate the last discussion on safety. So we did a lot of testing on the chassis dynamometer. And if you've never used a chassis dynamometer, they're amazing. So you run the motorcycle under full load. So you're watching this thing generate 36 kilowatts of heat. And so that's another way to mitigate risk, is that motorcycle has been tested under severe loading in terms of the drivetrain. So we had a motor blow up on the chassis dynamometer. It didn't lock up the wheel or anything like that. And if you watch the documentary, a lot of motors blew up and it didn't lock their rear wheel or anything. So there wasn't a safety. I mean, it was a safety issue, but it didn't cause harm to anyone when that happened. But the whole history of why people died, I don't know every single 200 reasons why people have died. There were 2 people, I think, that died the year we were there, and it was just crazy, random situations. I mean, sometimes I heard one of the stories. It was like there was a horse that jumped over a fence that then it was just like there's a chain of events that sometimes happen that then create a crash too. They're not always just rider errors. It's a lot of times it's this unfortunate situations that kind of happen. Yep, in the back.
For the battery packs, are they lithium ion, or what type of batteries are they?
Yeah, the ones that we used for Isle of Man were lithium iron phosphate. So there were these square pouches, and that at the time that was kind of where automotive companies were going, and that was kind of the interesting thing of that time. And I mentioned that a little bit, that people were like trying to figure it out. You know, you have Tesla that uses the small cylindrical cells, and so it seems like that's also kind of winning out in some ways. But the cells that we used were actually the large format pouch cells for the Isle of Man. And then Pikes Peak, we actually used a lithium polymer, almost like hobby grade cells for that bike. Yep.
Were there transmissions on either of these? Or did you find the motor speed match the sprocket directly to the rear wheel?
Yeah, so the question's about any kind of transmission. And so we just had direct drive, so it's like one sprocket in the back, one sprocket in the front. And that's what's the great thing about electric, is that normally you need a transmission to increase the torque, and with electric you get all the torque at low speed, so you don't really need one. There are certain companies that have put it on their motorcycle, but I think one of the appeal is that you don't need it. It just, you twist and go. So, but yeah, that's the main design variable that you have. Is there was a picture of me swapping out a sprocket, because once the bike is built, you can tune the motor controller settings and software, which really sets a few parameters, mainly related to current. But you just have that rear sprocket, and that's all. You can make it bigger or smaller. That's kind of your option. Yeah, it has to do with a trade-off, because the bigger you make it, the faster you accelerate in the rear. But the smaller you make it, the faster you go, top end speed. So that's actually some of the simulations I'm running now, is trying to figure out what would have been the optimal. Now knowing what we know, what would have been, and could we have used some technique, some simulation?
Why go to chain as opposed to the belt?
Yeah, that's an interesting question. So why to go from the chain to the belt? And that really has to do with that dynamic with the rider. So they just had their own preferences, and he just thought it was better. He said that he could really feel a lag in the belt, that when he gave it full throttle, there was a little bit of a lag just due to the elasticity of the belt. So you just have to trust that what he's saying is right. But there's a lot of that dynamic between the engineer and the rider, that is, it feels this way, and the engineer is saying, well, what the data says this kind of thing. And really the feels this way wins out usually, because kind of back to the safety, it's his life. I mean, it's he's the pilot. Yep.
Yeah, what training does a rider get? I mean, how does a person become one of these professionals?
Yes, super interesting question. So how does someone end up like that? Because yeah, we kind of dove into this world, like we're all these engineer guys, and then so the two personas, I'll explain. The Isle of Man guy, Alan Brew is his name. He grew up on the Isle of Man, so it's just in his blood. I mean, he's been listening to the howls of the engines his entire life. So it's just kind of part of the culture. It'd be like cross-country skiing here or something at the Isle of Man. It's just motorcycle racing is in their blood and in their culture. He is a lawnmower repairman, is his side job. So that's what he does, at the time at least. But passion is obviously a key ingredient to it, super passionate about it. The second rider was from Japan, Kishimoto, and he sleeps next to his motorcycles. So his wife is his mechanic. So he just loves motorcycles. He, I don't know, I think he gets his money through sponsorship and things like that. So, but they just live and breathe it. He goes to the track, and they pretty much do it as passion. They don't. They don't make a lot of money doing it. So, yep.
the writer at Isle of Man again, he obviously rode gasoline-powered engines prior to this electric.
Yeah.
What was his reaction to having that switch?
Yes, excellent question. So the question is, Alan Brew, he's been on the Isle of Man his whole life. Here he comes. These kids are coming along, giving him this electric thing. What is his reaction to it? So before I answer that, I want to even kind of go back to the safety one because that's related. Actually, the thing that was equally nerve-wracking, I said, oh yeah, there's been no deaths in the electric class. Well, I neglected to mention that in order to race in the electric, you have to qualify on a gas bike in the gas qualifying race. So our rider, even that whole dog chain thing, I was actually more nervous that he had to get on a gas Kawasaki something, and he had to qualify on a gas bike. And electric riders have died in that process. Wow. So that's actually the more nerve-wracking process because the speeds are higher. They have to do 6 laps. So anyway, that's kind of related to safety, but you're right, that kind of gets to what he has to do. And so he did, he qualified, he has to have a competitive time. They really want to show that, okay, this person is a competitive rider in our world of the gas bikes. So he has to demonstrate it. And then they say, okay, now you can ride the electric, a couple days later. So his reaction was, he actually started crying a little bit. He got teared up when we were up at the north side of the island. We were testing just because it was just, and even after, I think it was after maybe even he did one of the practice ones, it's just so quiet. I mean, that's what you hear from everyone. He's like, I could hear people clapping. And here's a guy that's been doing it. He was in his 50s, and he's used to just like, wah, wah, that loud noise. And he's like, I could hear people. They were clapping and yelling, and it was just, he's like, wow, it's amazing. So he thought it was pretty cool. Yep, in the back.
Now, they don't do any liquid cooling on those motors at all. Would the trade for adding a cooling system on for that, wouldn't that be an advantage and reduce the size of the batteries and also the efficiency of the motor?
Yeah, so the question is motor cooling and how would that help? So it would help in the sense that you could probably have a lighter motor for a certain amount of power. I mean, the big thing, motors are super efficient. They're like in the upper 80s or 90s, but when you're pumping out 60 kilowatts, even a few percentage points off that is a lot of heat to get off of a small surface area. So the Zero bike is air cooled. That's how they have it. You could liquid cool it, and we kicked around a few things. We had a couple benchtop demos. But yes, it would definitely help. It just is more complicated. So you have leaking and all this kind of stuff. But I think that's where it's going to head. I don't know why it wouldn't. I mean, gas engines are liquid cooled. It will allow you to get more power out of a certain size because you could get more power out of it. You can, it can generate more heat and you get rid of the heat. It wouldn't help you with battery energy at all. You still would need, it wouldn't save you energy-wise. It will just allow you to have higher power, but that which you'd need more battery for. But it won't. It doesn't increase. I mean, there's probably small improvements in efficiency, but not.
So you wouldn't gain any efficiency with.
I mean, it would depend on the specific motor and putting it on a dyno and seeing that. But that's in general, no, you wouldn't get a. It's mainly that, like, at least from a racing perspective, it's not about the couple percentage points different. It'd be like, I can now go from 50 kilowatts to 70 kilowatts continuous. That would be the main savings, which would mean you need more battery. Yep.
What is your prediction as far as the competition between gasoline motorcycles and electric? Will electric ever be able to outperform it?
Yeah, that's a good question. So I think Isle of Man and Pikes Peak are different. Electric has already advanced gas at Pikes Peak. So now the vehicles that win are electric in Pikes Peak. And motorcycles, I'm pretty sure, have the record too. It was a few years ago. It was a guy that was at Isle of Man. I met him. His bike didn't make it to the race because they were having some battery issues. But in the pits, I met him. And his bike ended up going to Pikes Peak, and I think they still have the record, or they're extremely fast. So that's kind of, I guess to answer your question there, is it Pikes Peak, it's already happened, so electric has already won. And it has to do with it, again, it's a torque. It's a shorter race, so its energy is not as big of a deal, and it's all about torque, and just electric motors are going to win. This is about the Isle of Man, so I didn't really actually... Yeah, I didn't really point this out, but that's an excellent question. So this shows from 1907, as I mentioned. This is the gas is shown here. This is the electric. So you can see the slope is much different. You could extrapolate and predict when you think it is. I actually don't know. Even just to show you as an example of how random some of these things are, like see how this point here they were going up and then the next year it went down, like in the electric. But it has to do with that hill that I showed you guys where the motorcycle gets airborne. So that motorcycle was in the lead, airborne, came up, he came down, and the bike shut off. And so he pulled off to the side of the road, and what's going on? Well, long story short, actually it's just a short story, the emergency button on the back of the motorcycle, which we had one too, just because of the inertial loads, closed and shut the bike off. So it's like all these little dots, ups and downs, like some of the small fluctuations are these random stories that, I'm sure they go back to the gas days too. But if you extrapolate, it looks like in a few years, but then the gas bikes could say, okay, now you got to do 6 laps because the electrics only do 1 lap right now. And so there's, you need to do battery swapping or fast charging or something. And that kind of gets back to the original slide, which I showed with fast charging, because that's what we were thinking at the time. Because originally they were going to have the electrics do multiple laps, but then they converged on just 1 lap. They changed the rules.
Why have that up? What's the explanation for the 4 years decreasing right after World War II? What I've been told is that something to do with gas regulations, even in the race, and gas quality and weird things like that. But it doesn't have to do with, and it might even have to BMWs in there somehow. But to answer it, I don't have the full answer, but I also asked it at one point and to a historian with motorcycles, specifically with Isle of Man, and he mentioned a few of those things.
You didn't allow superchargers after the war.
What's that?
Superchargers were not allowed after the war.
Something like with the regulations, so okay, they didn't allow supercharging, yeah. And that can do it, one change in the regulation, and then that's, yep.
I wonder if you comment on Makerspace culture, the culture of the student in your Makerspace to the culture of Sector 67 or other Madison public makerspaces.
Yeah, so the question is with the Makerspace and kind of the culture. I don't know Sector 67 super well. I've visited there. I think I can say for the culture we're trying to create here, which is just more on that student empowerment side, where they're really trying to take what they're learning in class and saying in an engineering course or maybe just a general design course, and feeling empowered to be able to make a project that either demonstrates what they learned or applies what they learned. But yeah, I think if you get into more of the community spaces like Sector 67, there's a lot of variety. They have a much more challenging situation in some ways because they're more of a community and engineers and artists and a wider range. So I think it is quite different, though, I think, being rooted more of an engineering program, because we support a lot of the academic curriculum.
Any more? If not, thank you very much.